Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the second part of hydro energy, and in this part we will concentrate on hydromechanical equipment, that is turbines, and different types of turbines we will discuss, that is impulse turbine, reaction turbine and components of these turbines, and then specific speed for turbines, then selection of turbines and turbine generator unit, component of generator, and then types of generator and type of gates. Hydromechanical equipment, as you have discussed, in this equipment, this type of equipment, kinetic energy of water is converted to mechanical energy and turbine is the major part of it. And in this case, when water falls on the turbine blade, it rotates, which is connected with the shaft, and the shaft is coupled with the generator for electricity production. We have already discussed it. Then water turbine is a rotary machine that takes energy from moving water, and flowing water is directed on the blades of a turbine runner, creating a force on the blades, and since the runner is spinning, the force acts through a distance, and this way energy is transferred from the water flow to the turbine. The turbine turns a metal shaft in an electric generator which produces electricity. The principal types of turbines are basically impulse and reaction type. So, impulse, maybe some examples are Pelton, Targo and cross flow, whereas reactions it is Francis and Kaplan. This Kaplan is basically axial flow turbines. Propeller, semi Kaplan and Kaplan, these are types of turbines. Now, we will see impulse turbines. What is this type of turbines? Here we see this is our penstock. So, water is coming and entering through this. So, this nozzle is there. So, through this nozzle the water is coming and getting entry into the turbine casing. And we also see here, so the governor can place the needle in the nozzle. So, depending upon the nozzle position, the flow of water can change. So, the main feature of impulse turbine is that an impulse turbine is driven by a high velocity jet or multiple jets of water caused by nozzles. So, this nozzle is creating jets to convert entire pressure of water into kinetic energy. This is the main feature of this impulse turbine. The jet pushes on the turbine's curved blades. So, these are the curved blades. This jet pushes on these curved blades, which changes the direction of flow, hence causes a force to act on the turbine blades. So, here the flow is going this direction and it is changing this direction, the water is, at the same time the blades are forced to move and get some circulatory movement to the rotor. The force acts through a distance and the diverted water flow is left with diminishing energy. So, this water which is getting out, that is called tail race, then that loses its energy which was available in the upstream of it. If the load on the turbine decreases, that means I need some less electricity, the load on the turbine is decreased, then we have to reduce the water flow, and that is done by the governor by pushing this needle into the nozzle. And these impulse turbines are often used in very high heat applications. And this Pelton turbine, one example of this impulse type turbine is Pelton turbine. You see here, the blades are mounted in this rotor in the runner, both sides we see the blades are attached and half of the blades it is shown. So, it consists of a wheel with a series of split buckets set around its rim. So, this is our rim. So, series of buckets are connected to this rim. A high velocity jet of water is distributed tangentially at the wheel. So, at the wheel we tangentially, just like here, tangentially distributed to this wheel, and the jet hits each bucket and is split in half. So, jet is hitting this bucket and two half it is splitted, so that each half is turned and deflected back almost through 180 degree, and nearly all the energy of the water goes into propelling the bucket, and the deflected water falls into a discharge channel below. So, just like this which is shown here, it is falling here in the discharge channel. So, this is the figure photograph of Pelton turbine, and another type of impulse turbine is turbo turbine. So, here also very similar, but some design is different. So, you see that this diameter is lesser than this which is having here. So, it is similar to the Pelton turbine, but the jet strikes the plane of the runner at an angle that is typically 20 degrees. So, this is made some 20 degree angle. So, water which is coming there, that is striking the plane of the runner at 20 degree to 25 degree angle, so that the water enters the runner on one side and exits on the other. The turbo turbine can have a smaller diameter runner and rotate faster than a Pelton turbine. So, just I have discussed, this diameter is less and this design is also different, there is some angle 20 to 25 degree, and so it can rotate with a faster speed. And then cross flow turbine. So, this is showing a cross flow turbine. So, what we see here, it is a drum like rotor with a solid disc at each end. So, each end we have some solid disc, here is one solid disc, here is one solid disc. So, these two solid discs are attached with these sluts. So, that is gutted shaped sluts. So, these are joint, and a jet of water which is getting entry here, a jet of water enters the top of the rotor through the curved blades, these are the curved blades, emerging on the far side of the rotor by passing through the blades a second time. So, water is going there and again it is one time again it is going through this. The shape of the blades is such that on each passage through the periphery of the rotor, the water transfers some of its momentum. So, when the water is passing through this, it transfers some momentum, and before falling away with the little residual energy. So, when it is falling from this rotor, the water loses its energy. So, here we see these are the different parts of this turbines. Here air venting valve, air venting valve is shown here, then distributor. So, this is distributor and 3 turbine casing. So, all these are casing of the turbines, and the grey color, these are the casing, and 4 is our runner. So, this is our runner, this is the case here we are having the runner, and then removable rear casing 5, this is your removable rear casing, and blades, these are the blades which are attached with this runner, and then water flow it entering here and it is going to this side. So, this is very important, here the water is coming and it is going. So, here it is moving through the blades, again it is moving to the blades. So, it is going that way, and then it is our shaft. So, then we are coming to reaction turbine. So, what we have seen in case of impulse turbine, the water flow passes through nozzles and hits the blades of the turbine. In reaction turbine, the water enters the runner partly with pressure energy and partly with velocity head. So, they must be encased to contain the water pressure, or they must be fully submerged in the water flow. So, there may be the possibilities in this case, and in this turbine the runner blades rotates with respect to guide vane. There are some guide vanes which controls the flow, and that flow controls the speed of the blade, as the sudden decrease of load takes place, means the turbine needs some less RPM of the turbines blade, then the guide vane limit decreases the water flow. And most water turbines in use are reaction turbines and are used in low and medium head applications. Some examples are Kaplan turbine and Francis turbine. So, propeller type of turbines, that is Kaplan turbines. So, propeller type turbines, that is Kaplan, they are similar in principle to the propeller of a ship, but operating in reversed mode. How it operates? We see here we have guide vane. So, these are the guide vanes. So, water will come through it, these guide vanes will allow the water to come to the blade and it will give some movement to the runner. So, as a set of inlet guide vanes admits the flow to the propeller, and these are often adjustable so as to allow the flow passing through the machine to be varied. So, the flow is varied by the guide vane. Now, Francis turbine. So, it is essentially a modified form of propeller turbine in which water flows radially. So, here water is coming radially inwards into the runner and is turned to emerge axially, then it is going this direction, it is going there. So, this is the flow of the Francis turbine, and for medium head schemes the runner is most commonly mounted in a spiral casing with internal adjustable guide vanes. So, these are the guide vanes, internal adjustable guide vanes. So, these are the different types of turbines which are used in hydropower production. Now, we will see how to get the information about the different types of turbines. So, we have some parameter that can be compared to guess the performance or efficiency of the turbines. So, that is called specific speed. So, that specific speed for various types of hydro turbines we will see here. So, what the specific speed is? So, specific speed as per the expression it is Ns is equal to n root of p by h to the power 3 by 4. So, n is the RPM of the turbine, p is the rated power in kilowatt and h is the head in meter. So, this is the mathematical relationship of specific speed. So, what the specific speed is? So, that we will see now. So, the specific speed value for a turbine is the speed of a geometrically similar turbine which would produce unit power, that is 1 kilowatt under unit load, that is 1 meter, unit head under unit head, that is 1 meter. So, this is our specific speed. So, this specific speed is given by the manufacturer of the turbines, and we can say this is the maximum capacity of the turbine to perform or maximum efficiency of the turbine. Now, we will discuss how the turbine can be selected. So, turbine selection depends upon some factors. One is your head requirement, another is your what is the requirement of the power production. So, what is the capacity of the power plant, what is the head available and what is the flow available, what is the flow available, what is the head available and what is the capacity we are expecting from the plant. So, that will help us to decide what type of turbine can be chosen. So, this graph shows us some information. So, this is your say this yellow line, yellow area, this indicates Francis turbines. So, here we have head in y axis in meter, flow meter cube per second in x axis, and these black lines indicates the capacity of the plant. So, 0.1 megawatt, 1 megawatt, 10 megawatt, 100 megawatt, 1000 megawatt, and this is the zone where we can recommend Francis turbines. This is the zone, the blue color, when we can go for Kaplan turbines, and this is the zone for which we can go for Pelton turbines, and this is the zone for which we can go for Turbo turbines. So, these are the different informations, these are the informations which help us to select a turbine type. for our particular application. Now, we will see the components of turbines. What are the components of turbines? Now, we have seen that is the it is attached to the penstock. So, penstock that is the large diameter tube through which water from the dam comes to the turbine inlet, and it is made of steel. And then spiral casing, that is it is a closed passage whose diameter gradually decreases along the flow of direction. Area is maximum at inlet and nearly 0 at outlet. So, this is your spiral casing, and to maintain constant flow rate numerous openings are provided to this, and the purpose of casing is to distribute water over guide vanes and prevent formation of eddies in the turbines, and made of cast steel or concrete. Then guide vanes, those are also very important to control the flow of water into the turbines blades. So, they are aerofoil shaped vanes fixed between two rings, and they convert a part of pressure energy into kinetic energy, and each guide vane can rotate about its pivot, and hence it also serves to direct the flow at design angles to the blade runners. And the runner rotates due to impulse and reaction effects, and it is made of cast iron, stainless steel or bronze. And draft tube, it is gradually expanding tube which discharges water passing through the runner to tail race, and generally its diameter increases in flow directions. And governing mechanism are there, just we have seen that if needed the needle in the nozzle will be placed to reduce the velocity in case of impulse turbine. So, here the it can, so governing mechanism, it can change the positions of guide vanes to vary the flow on turbine, either guide vanes position or the positions of the needle in the nozzle. So, that way for impulse turbine. So, this helps. So, these are the different parts of the turbine which helps to perform it in most effective way. And now, in the turbine, the mechanical energy which is produced, that has to be converted to electrical energy. So, turbine generator unit or coupling of turbine in generator is very, very important. So, the role of the turbine is to transform the energy of water or steam or wind that we have discussed in the previous classes also to mechanical energy that will make the generator spin. So, the generator transform the mechanical energy into electricity. In hydropower plants, the combination of generator and turbine is called a generating unit. So, this is the generating unit, and we will see some terms here, that is say electric generator, we will say this is a transformers and pylon. So, as the water rushes through the turbine, it spins the turbine shaft which is coupled to the electric generator, and the generator has a rotating electromagnet called a rotor and a stationary part called a stator. So, rotor and stator are the main part of the generator. The rotor creates magnetic field that produces an electric charge in the stator. The charge is transmitted as electricity, but this electricity voltage may not be that high. So, the setup of transformer increases the voltage of the current coming from the stator, and the electricity is distributed through power lines, that is called as pylon. These are the parts of turbine generator unit. And the component of generators, if we see, then major components are the stator, rotor, upper bracket, lower bracket, thrust bearing and guide bearings, the bearings is required, and spin ring, slip ring and brush assembly, and air coolers, brakes and jacks and stator heaters. So, these are the parts of, so here the turbine, and this is the stator and this is rotor, this is the rotor. Now, how can we calculate the power generation? If it is the data available in FPS system, the power generation can be head into flow into efficiency by 11.8. So, power, electric power in kilowatt, and then the distance the water falls in feet, and then flow is in cubic feet per second. So, then this formula is used, and efficiency, Then this term efficiency, how well the turbine and generator convert the power of falling water into electric power. So, basically it will be having combined one. So, turbines and generator. So, this can range from 60% for older and poorly maintained hydropower to 90% for newer and well maintained plants. 11.8 is index that converts units of feet and seconds into kilowatts. So, this is a formula which can be used for the power calculation. For an example, as an example, let us see how much power can be generated by the power plant. The dam is 357 feet high, the head is 235 feet, the typical flow rate is 2200 CFS, that is cubic feet per second. So, let us assume the 80% efficiency of the turbine. So, in this case power is equal to head into flow into efficiency by 11.8. So, here head is 235 feet and then flow is 2200 CFS and efficiency is 80%, that means 0.80. So, divided by 11.8. So, that is equal to 35,051 kilowatts. So, that is equal to this much is the power generation capacity of the plant. Then as we told that efficiency of the system depends upon the efficiency of the turbine, the efficiency of the generator, efficiency of gearbox, and weighted average efficiency is the multiplication of this and this. So, for example, 88 to 94% for turbine efficiency, 96 to 98% for generator efficiency, gearbox is 98%. So, weighted average efficiency we get 75%. And there are different types of gates for hydropower. So, that is radial gate and slide gate and circular gate, that helps the flow of water through the gates. So, this is the radial gate and this is slide gate, these are the circular gates. So, there are different types of gates and different types of valves also used in this plant. So, up to this on hydro energy production. Thank you very much for your patience.